All right, so day 4, limits at infinity. Now we said that when when y is going to infinity, we say the limit does not exist. Because x is approaching a specific value and the value of our function is going off to infinity or negative infinity. Okay? This is different. These are limits at infinity. So what we're doing is we're taking the limit as x approaches infinity or x approaches negative infinity. And basically what we're dealing with here is end behavior. You guys remember looking at end behavior with our rational functions and whatnot. Here are a couple of things that are super helpful in this case. First of all, when we had polynomials, remember they went off to infinity one way or the other based on our end behavior. We had this leading coefficient test. If the leading coefficient was positive, the right side went up. If the leading coefficient is negative, the right-hand side of the polynomial goes down. And then the degree of your polynomial, whether it was even or odd, determined if the left side was the same or the opposite. Okay? So if we had, say, a positive 3x to the 5th, blah, 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 on the right-hand side it would go up because 3 is positive. On the left-hand side, the degree is odd, it's 5, so the left-hand side is going to be going down. And there's some other stuff in the middle here, but the end behavior is one thing that we could take note of pretty easily. That's what's going to be helpful in this case, right? Another thing is the rational functions and the horizontal asymptotes. Okay? One of the things with the horizontal asymptotes is that they are the limit as x is approaching infinity or negative infinity. Okay? If you have a rational function, the value that function is approaching is the asymptote, the horizontal asymptote. So this is where Bobo-Botten comes in. All right? You remember Bobo-Botten? Bigger on the bottom. If the degree is higher on the bottom in the denominator, then it's f of x equals 0. If the higher degree is in the numerator, that means you don't have a horizontal asymptote, and that means it's going to go up to infinity or down to negative infinity. And what would we say about the limit in that case?
Does not exist.
Does not exist. Okay? But then you have when there's an equal degree in the numerator and denominator, the limit is the ratio of the leading coefficients. All right, so let's see that again and relate it to limit here in this case. Okay? As we are looking at rational functions that we're taking the limit of as x approaches infinity or negative infinity, let's say that we had one like this. We have the limit as x approaches infinity of, say, an x cubed plus 5x minus 3 over an x squared plus 4x plus 3. It's bigger on the top, so there is no horizontal asymptote. Okay? Botten. So therefore, the limit does not exist. Because this function, if there's no horizontal asymptote, it's going to go up to a positive infinity or down to negative infinity. Either way, we'd say the limit does not exist. Okay?
What is bottom stand for?
Bigger on top.
Bigger on top, none. So you can think of it in terms of the limit too. The limit does not exist.
Big zero.
Bigger on bottom, 0. Okay, so that's the second one. The degree of the denominator, the bottom, is bigger. Then the limit is going to approach 0. Okay, so this is the Bobo part. All right, so we have the limit as x approaches infinity of, let's say it's x squared plus 4x plus 3 over the x cubed plus 5x minus 3. And because the denominator has the bigger degree, this whole thing is going to approach 0. Okay?
So this says, is this just used as limit is infinity?
Yes, this is just for when the limit is when x is approaching infinity or negative infinity. Okay?
It's not about the possible.
Not for these rational functions, because they'll be approaching the same thing. Remember the horizontal asymptote, you approach it on both ends. There are some functions, like say an exponential function, where you have an asymptote you're approaching on one side, but on the other side you're going off to infinity. So for those ones, you have to think about your parent functions and whatnot, and see what's going on. Okay? If the degrees are the same in the numerator and denominator, okay? So in this case, let's say we had the limit as x approaches infinity of 3x squared plus 5x minus 7 over 7x squared minus 9. Okay? It's just going to be 3 over 7. Yeah. Okay? So here, you use the ratio of the leading coefficients. Does that make sense? So, pretty easy. Now, you might be wondering here, why in the world can I just ignore everything else? I mean, what if there was like this one's approaching 0. What if this was x squared plus 4x plus 1,000,000? Alright, that's going to make that a lot bigger, right? Well, how is it still going to approach 0? The reason is, as x approaches infinity, even 1,000,000 becomes so tiny comparatively that it's not worth anything. Okay? So, I mean, think about it. If I had, a million squared is a whole lot bigger than 1,000,000. It's trillion, it's billion, trillion. It's 1 trillion as opposed to 1,000,000. 1,000,000 out of a trillion is nothing, okay? It's 1/1000th. Or no, 1/100,000th. Alright? So, it's really, nothing. No, it would be 1/1,000,000th. If I squared 1,000,000, then it would 1,000,000 would be 1/1,000,000th. Alright, but anyways, that's why the rest of this is insignificant. Same thing down here when they're the same. When they're the same, a 5x and a minus 7 are really insignificant compared to infinity squared. Okay? And really what happens, you can think of it like this. If you kind of think of it as direct substitution, okay, the rest of this is insignificant because it's so tiny. Infinity squared over infinity squared is 1. So it's just 3/7. Okay? What? Well, anything except 0 divided by itself is 1. So,
Sure.
okay?
Wait, so why would you be able to use this all the time?
What do you mean all the time?
Like, for the last, we went through synthetic division and everything.
Well, there x was not approaching infinity.
Oh.
See, if x were approaching 1, then yeah, this 7 and 9 would be significant values there. If x is getting enormous, 7 and 9 mean nothing, okay? So. Now, don't forget the limit theorems that we had, okay? Don't forget the limit theorems. This is why we started with this before. So here we have the limit as x approaches infinity of 7 plus 3x squared minus 5x plus 1 over 4x cubed plus 3x minus 7. Okay? So, if I'm doing this using my limit theorems,
Oh, you can pull it out.
I can separate this. Limit as x approaches infinity of 7 plus the limit as x approaches infinity of all of that. 3x squared, that's 5x plus 1 over 4x cubed plus 3x minus 7. Now, what's the limit as x approaches infinity of 7?
7?
It's 7. It's a constant. Remember, the limit of a constant is the constant. So that equals 7 plus,
3/4.
0.
what is it, 3/4 or 0?
Oh!
Bobo, yeah, bigger on bottom? 0, okay? So that whole thing just equals 0, so the limit here equals 7. Now, let's look at the next one. What limit theorem can we use for this one? Guys?
They're equal.
6 over 4.
6 over 4.
To the 3 over 2.
Okay, but that whole thing is to the 4th
So
power.
you can
So
pull it
6
out.
over 4 to the 4th?
I think
Is
it's
it
not.
3 over 2 to the 4th?
Yes and yes, okay? So look here, remember our limit theorem that said if you have the limit of something raised to a power, instead you can take the limit first and raise that to the power. So, like you guys said, 6 over 4
3 over 2.
to the 4th, yeah, it is a little easier to do 3 over 2 to the 4th, that's 81/16. Okay? 16th, wow. Yes, 16th. Went a little dyslexic there for a second. Alright, 81/16. So, here we have a little bit of practice. Now, notice here, you're matching, and the whole point here is you might say, well, wait, where are the limits? Well, the limits are the horizontal asymptotes, right? Okay, so look at, what would my horizontal asymptotes be? Look at the end behavior of your graphs here, and then really go ahead and identify, I know you're matching the graph with the thing, but go ahead and write down what the limit as x approaches infinity would also be, okay? So for each one, the limit as x approaches infinity of f of x equals what? Alright? Once, by the time you match the equation with the graph, it should be pretty obvious what that limit is, okay? And then there's some other practice as well, same idea, okay? Use those rules and find your limits as x approaches infinity, okay? So let's use the rest of our time here to work on these. You can work in groups or on your own.
Can I get my phone?